Rishabh, join.
Yeah, good evening, sir.
Good evening. Join. Okay. 1, 2, 3. Okay.
Uh, Sir, tomorrow your class will be from 10 a.m. to 11 a.m.
Actually, I want to
Uh,
change also because I don't. I have some other work at 10:30.
okay.
So you tell me some
Actually,
other time.
sir,
Can you just make it at 12
tomorrow,
to 1? 12 to 1 is okay.
uh, sir, tomorrow we have a alumni meet from 9 to 11 a.m. Sir.
Okay.
So it's
Evening is fine.
mandatory to. Evening this time is fine, sir. 6:30 to 7:30 if you are free. Other than after 11 a.m. whenever you are free, you can take class, sir.
I am free tomorrow. So around after 11 means 2 o'clock we will take it 2 to 3.
2 to 3.
Uh,
What about evening, sir? 6:30 to 7:30?
6:30. I think I committed to someone. That's why I put it in the
Okay,
morning.
okay, sir. 2 to 3. It's fine. Yeah,
Huh?
11 to 12. Yeah, 12 to 1 also fine, sir. 12 to 1
Uh,
again,
12 to 1,
if possible.
I'll change it to 12 to 1. Okay?
Okay, sir. Okay.
Okay. So let them come. I'll also announce. Huh? Others.
Okay, okay.
Only
Oh, sure, sir.
only
No,
little
sir.
group.
It's alumni meet for everyone, sir. This is for everyone.
That's okay. But that is afternoon you're free only, no?
I think others also, sir. There will be no classes and
Okay, okay.
that's. Uh, uh, I have to ask others also, sir. Maybe
So
someone
we'll,
has some work.
they're joining, right? So we'll ask him. We'll ask them.
Okay, sir.
So, so any questions? Previous thing? Any questions?
No, sir.
Just have something to see. Okay.
Sir, have you contact with Nikhil, sir, regarding offline classes from Monday to?
No, not yet. Not yet.
Oh,
Monday
actually,
anyway.
today I have.
Monday anyway. See, we'll. I don't know exactly. I'll contact him tomorrow.
Hmm,
Okay. So
okay,
otherwise we'll have online on Monday. Monday sometime I'll come and there, and then Tuesday anyway all offline we can have our classes, usual class, right?
okay, okay, sir. Actually, today I have contact. I informed to Nikhil, sir, कि you are coming on Monday. Sir,
Uh,
when you will be reach here, sir, on Idol, sir, what time?
I think morning sometime flight is in the morning, no? Afternoon, almost evening only. Sometime 2,
Okay,
3 or 4.
okay,
I'll have to two
okay.
flights. No? It's just 2 flights I
Yes,
have to take.
yes, sir. I think
Guwahati,
Chennai to
Guwahati,
Chennai.
same.
Yes,
Yeah,
sir.
I think
Chennai to Guwahati.
around 2 or 3, 2, 3. If I take it, I may be reaching 4, 5 evening. By evening only, I'll be reaching.
Okay, sir. Okay, sir. Oh, sure.
Okay, so I don't know where they kept also. So I'm going to stay. For me also first time. So anyway, we'll meet sometime. We'll have 4 hours at least. Okay.
Yes, sir.
So
No
we'll
issue, sir. We can 5 hours also, sir. Actually, I am thinking that you will be here in morning, sir, on Monday, so that
Monday
we are
morning
free
anyway I'll
on.
be there. Monday I'll be there.
Okay, sir.
Okay. So where is your this PhD student is there? No, what is his name?
Uh, in Amul, sir. In Amul.
Joining these days.
No, sir. Maybe he is busy in some other work.
Okay. 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 Earlier he used to.
I think maybe he say don't know also this extra classes also. I think he is in this group or not. I don't know, sir.
Oh, okay. Okay. I think the majority joined, right? So now we can start.
Yes, sir.
Okay. So we are planning. So what we are going to do today is we'll try to look at the flows. Okay, so before that, I want to tell you something. So something if you have UR, okay. So just remark. Let me put it this way. if you have UR component, right? So UR component, UR and U theta, that R cap direction, what is the velocity, and theta cap direction, you have a velocity, UR and U theta, right? So UR, U theta components, you know. So if UR is positive, okay, so what exactly, suppose you look at some thetas, for example, you have some theta, no? So what is the meaning of this? So flow is actually moving from the origin. That is the meaning of this, okay? Flow is moving away from the origin. By this, I think, you can easily guess how the flow is moving, okay? So if UR is actually less than 0, so flow is moving towards the origin. Okay, so similarly, if U theta is positive, so what is the meaning of this? If U theta is positive, can you guess? If U theta is positive,
then it's rotate also, sir. Flow is theta is not fixed in this case, no?
it is actually anti-clockwise.
Yes, sir.
Anti-clockwise direction. So it only tells you the direction, okay? So if this is positive, basically, so you're basically going anti-clockwise. So moving because theta is going from 0 to 2 pi, it is, and it is positive means it is increasing function. So that way, okay? So you are going with the theta. So that is the meaning of this. So similarly, if U theta is less than 0, you keep them in mind so that you can easily guess how the direction of the flow and how actually it is, you can, how it is going to flow, which way it is going, and where is it going. Those things you can fix it. Okay. So so if this is less than 0, so you can say it is clockwise. Flow is clockwise. So keep them in mind, and you just you try to look at the earlier flows. You will understand based on this one. Okay. I think some issue. So today what we do is we'll try to look at, as I told you, so there is a uniform flow. So let's consider. So what is the flow that you have? So, and okay, one more point that I want to make it clear. If you actually see this fourth, so fourth flow or fifth flow, whatever you call it. So if n is let us say take equal to 2. So what is that flow that you have? N equal to 2. N equal to 2. Can you just give me what is U or U theta?
A2 2 R square and cos n theta, cos 2 theta.
Okay, U theta is minus.
Maybe 2. Sir, 2A2 is there. Yeah, only A2, sir.
Let me see your.
Sir, only A2, sir, not 2. Only A2. 2 is not here, sir. A2 R square cos A2 R square cos 2 theta, sir.
That is
If n equal to
23 or 24. 23 is not there. 22, did I write? Where exactly I have written? So 22 maybe. Yeah, so fifth one, no? So fifth is fifth flow. So this is the fifth one that we have done. Okay. Flow example, flow 5. N equal to 2 when you consider 2A to R. R only, no?
all.
There's only one R. So there's only R cos 2 theta. And U theta is minus 2A to R sin 2 theta. Okay. So what is that I want to tell you? So okay, so what is this flow? So this flow, if you actually see, this is your planar extensional flow that I told you. No, you actually try to calculate. It is you going to get xy equal to constant, right? Your psi of xy equal to simply x into y, isn't it? That you can easily calculate. This is what we have
Yes.
written. So this is the one. So if you actually see xy equal to 0, suppose look at this. Look at psi of xy equal to 0. So what is that xy equal to 0? So this is the flow usually. Okay. The direction you don't worry. Based on this, you can easily see. So now you can apply these whatever those principles above one, which direction it is going. Okay. So the direction you can easily see based on your theta. So theta between 0 to 2 pi, what is sine to theta? So it's this u theta is negative or positive. That way you can decide your direction. This is anti-clockwise we are seeing, no? This is anti-clockwise. Okay. So anti-clockwise means this is positive. As you can see, between 0 to pi by 2, what is the value? So negative, no? Clockwise direction, isn't it? But
Yes, sir.
whether u theta is clockwise or anti-clockwise, minus and sine 0, sine 0, 0, sine pi by 2 means sine pi, right? Sine pi is, it's all positive, right? It's going up and it's all positive, right? So which way it is going? Is this clockwise or anti-clockwise?
Sir, anti-clockwise.
This is anti-clockwise, right? So is it positive? U theta is positive here in this case? No, right?
Then sir, it's in the clockwise,
0
sir.
to pi by 2, 1, it should be clockwise, right? So clockwise means what? So it should be opposite direction, right? It should be this way, isn't it? We wrote wrongly in that 20-second file. So you just check it. So you see whether it is moving away from this. So if you are asking for u, what is ur? Ur is cos 0 to cos pi. What is the value? Or just take cos 0 to cos 2 theta means 2 pi by 2. So
Sir, excuse me, sir. Sir, I have checked, sir. U r equal to a to r square cos 2 theta, sir. For our general form is a n r power n cos n theta.
yeah, ur is nan r power n
A,
minus 1 cos n theta. That is ur, right?
yes, sir. Yes, sir. Yes, sir.
U
Yes.
theta is minus an r power n minus 1 n into sin n theta. This is fine, I think.
Yes, sir. Yes, sir. Oh, actually, I confused. Yes, sir.
Yeah, you just check and you look at this. These four. This is another way of seeing the direction. You will learn anyway while doing the complex flows also. Okay. So based on this, we can easily see this one. So otherwise, you just convert this into usual coordinates. Okay. So how do you see the direction of the flow? How do you see the direction of the flow? Put your u equal to, so what is that you get here? So u equal to, what is that you get? U equal to 2a2x, right? That you need to calculate, right? You need, if you calculate, as I told you, don't substitute r cos theta equal to x like that. So in Cartesian coordinates, this is what you are getting. So that u is positive, so that means u is positive, v is negative. So that means this is this direction only correct, isn't it? If you draw a line, the tangent means this way, no? If this direction, this is your tangent. So what is the tangent? Basically, it is u is its direction is u is x direction, it is positive, y direction it is negative, right? So this is this direction. So but u theta, what happens to u theta? This may be a little this is some small confusion, right? You fix it. So this may be clockwise and this may be anti-clockwise. Okay. So if you actually see this one, this makes it what? This is like clockwise, right? Isn't it? You just fix it based on that. I think maybe this you need to question. Okay. You just verify with your standard flows and then fix those things. There is a convention.
Sir, yes, sir.
Ah.
This was in second coordinate pi by 2 to pi, sir. Then our sine theta goes from pi to 2 pi, sir, because to sine 2 theta is there. That's why, sir, it's anti-clockwise. Then this will be in this direction, sir. U theta is positive, sir.
U theta is positive means anti-clockwise, but it is we are going in clockwise, right? We are going actually clockwise. I think this, if it is positive, it should be clockwise, right? You see, the best way to see is your look at your vertex flow. That is the easiest thing, no? You know, if M is positive, it is going like this. We have already seen, right? Isn't it?
Yes, sir. Yes, sir.
That you based on that, you just check it. Okay, so if it is there, you just, if you know this question marks, you can fix it whether it is anti-clockwise or clockwise. If it is clockwise, that here it will be anti-clockwise. So the direction you can fix it based on that one. Okay. Okay. So the another point that I want to convey is look at this one. What is this meaning of psi equal to 0? This implies xy equal to 0. That is, that will give me first stagnation points. That is x equal to 0, y equal to 0, isn't it? Or so all the stagnation points are basically the x-axis, right? Or x equal to 0 or y equal to 0, isn't it? And x positive. X has to be finite and y has to be finite. In that case, this will be 0, right? Psi equal to 0. So that means all these are of x and y axis. So when you consider, so that's why you don't get the streamlines on the x and y axis. This actually separates, right? This x axis, y axis basically separates all the flows. That is why these are actional. This is the flow between these angles, 0 to pi by 2. So when n is greater than or equal to 3, that is what you are seeing between the wedges. All the flow is happening between the edges. But direction based on your u theta, you decide. So, and also you can also see this one, you look at that, it will be symmetric, no? If it is, then you see here, psi equal to 0 here, psi equal to 0 here. Okay. So if it is between psi, what is the theta here? This is your theta equal to 0. And this is your theta equal to pi by n, right?
Pi by 3. Yes,
pi
sir.
by n. So pi by n. So the exactly half will be theta equal to pi by 2n. So it is actually symmetric. If you actually see your u and v, that is actually symmetric. You can easily see that is symmetric. The flow will be symmetric, and you can see the direction based on that u theta and same whatever conclusions based on this ur, whether it is positive, negative, between this 0 to pi by 2n, whether it is positive or negative. Okay, those things you can easily fix it and see. Okay. So the point is psi equal to 0 will always give you the flow separation. That's what is I want to the point and to make a point. Now let us look at a new flow that we were thinking of doing. So that is you consider, let's make it phi equal to, I'm just making two combinations, right? Phi1 plus Phi2. So what is my phi? Phi equal to, Phi1 will be uniform flow. Let's make it Ux. Okay. This is uniform. What is Phi2? Phi2, let's take it. Earlier I told you, last class I told you that if you take doublet, you will get flow past cylinder. Okay, so to get that feeling, so we'll first start with the source here. So this is the source. Source is means what? What do you have? Q log pi, right? Log R. Q log R divided by 2 pi is your source. Source means Q is positive. Okay, so basically what you have is, this is your uniform flow, and you have a source. What is the source that you have? All these directions is going out. These are your streamlines. If you combine this one, so if you put this one, so this is the source at 0. So this is your 0. This is your x and this is your y. This is at 0. At 0 you have source, and from far from infinity you have a uniform flow is coming from infinity. Okay. So if you consider this one, what is that? Now you write it in the polar coordinates, phi of r theta. So wherever x and x is there, you put r cos theta. So u r cos theta plus q into Q divided by Q. So now this is your phi, right? So phi is Q ln R divided by 2 pi. So this will give me immediately my UR U theta components. What is UR components? Dou phi by dou R. So dou phi by dou R is simply U cos theta plus Q by 2 pi R. And what is U theta component?
Dou phi by dou theta.
1 by R dou phi by dou theta. Okay. So 1 by R, if you do 1 by R dou phi by dou theta. So that will give me U R goes U sin theta, right? Minus sin theta. And this quantity will be anyway 0. So this is what it is, right? Now, how do we understand this flow? To understand the flow, we use the stagnation points. Stagnation points passing through these points, you try to look at your streamlines. Okay, so let's look at this way. So why we are using this one to understand this one? Because you see, this way also you can look at it. U sin theta direction only tells you, right? Sin theta direction, based on the direction you can tell which direction it is going, but you don't know, right? So this UR thing is like going as R is always positive, right? So what it tells you, UR is always positive. Theta between 0 to pi by 2, for example, 0 to pi by 2, this is always positive. This is positive. So what happens in the first quadrant? What is happening? So that means in your here, if you actually see this side, only in this quadrant, this area, what happens? It is UR is basically positive, so it is moving away from this origin, right? Moving away from the origin. That's what it tells you, no? If you believe whatever I said, if UR is positive, this is moving away from this origin. So from this is origin. So here moving away from origin, but you don't know the curves, right? So curves you don't know because you have a UR component, say UR cos theta and Q ln R. So ln R is not easy to understand. So to see these things, we'll try to look at the stagnation point. So stagnation point means UR equal to 0 and U theta equal to 0 simultaneously. Okay. So it's stagnation points. So I'm just writing S points, okay, equal to 0 implies. So what is that you get? So what is U theta? So U cos theta, what is UR theta? So let's call this U cos theta plus Q by 2 pi R equal to 0 and minus U sin theta equal to 0. So what is this gives you? So this first gives me U sin theta. So U cannot be non-zero. So sin theta will give me what?
Theta equal to n pi, sir.
You have 0 to, what do you have? 0 to 0 or pi, right? So this
Yes,
gives
sir.
theta value 0 and pi, both the values. Now try to put cos theta. What is the cos theta value?
So at
Right?
0 this one and at pi -1, sir.
Yeah, it is -1. So what is your R there? So Q by 2 pi R equal to minus U cos theta implies R equal to Q divided by minus Q divided by 2 pi U cos theta, right? This is what is your R. If you take
Yes,
theta
sir.
equal to 0, cos theta is 1 and Q is
Yes, sir.
positive, so then it will be negative. R is negative. That is not possible, right? If theta is 0,
Yes, sir.
R is not possible, right? So you try to write separately, so you will understand. So that's what you get. So this implies R is R equal to minus Q divided by 2 pi U cos 0 is 1. Okay, this is negative if theta is 0, not possible. So that is not possible. So this is ruled out. So theta equal to pi. Look at theta equal to pi now.
Just Q by 2 pi U, sir.
That is Q by 2 pi U. Yeah, this is what is your stagnation point. So this is possible, right? R is this one. Okay. So at theta, you have this one. So this is what exactly where Q is positive. So theta equal to, so the finally stagnation points are, okay, basically only one, okay? Stagnation point where there is no flow is equal to R comma theta, no? R is Q divided by 2 pi U, which is positive, and theta equal to pi. So this is your stagnation point. Now you can feel it, no? So if you
Yes, sir.
if you actually see it, draw the thing. You have a source here, and this is at this point. Q is positive, right? R. Q is pi. I mean theta is pi. So your point is here, right? That means Q by, so this is this distance is R, which is Q divided by 2 pi I. So this point is basically Q divided by 2 pi U, comma pi. This is your point. This is your stagnation point. Okay, and this is your origin. So what is that you have? Basically, see earlier you have these kind of, this is what you have now. These are the things you have. So basically, if you draw this, so it goes like this. This goes like this. Okay, and finally, anything that passing through, and it basically becoming like that. It won't cut, right? So it won't cut, and eventually, can you feel that? Yeah.
Yes, sir.
So before you see inside, that is what is maybe happening inside. Okay, so you don't look at this right now. So what you do is you just check this now at through the stagnant. So find a streamline passing through this point Q divided by 2 pi U and pi. What is that one? What is that one? That line is basically psi at x comma y. It is stagnant now. U equal to 0, right? So U equal to 0 means U equal to 0. Stagnation point means what? What is the velocity there?
0, sir.
If you want to find the velocity, that has to be psi has to be equal to, what is your psi? First of all, you find the psi or the flow. So what is your psi for this flow? UR is this, right? UR is this, U theta is this. Calculate your streamlines. Okay, I'm going to give you some exercise here. So what is how do you find the streamlines first of all?
So calculate psi using dash formula, sir. U r equal to 1 by r dou psi by dou theta, and U theta equal to
dr divided by UR equal to R d theta divided by d U theta. You solve this, right? So this, if you solve it, dr by, what is that you have UR? I think I'll not do this. You do this in exercise, okay?
Sir, can we do like that one also, sir? Like if we know psi.
You can directly also solve and get it. Okay. So the best way is, okay, you exercise. You do the way you like, whatever way you like, you do it. Find streamlines. Okay. So we'll only verify it. Okay. So let's exercise. Answer. Let me write it as that's an exercise. Answer is psi of r theta equal to U r sin theta plus q theta by 2 pi. Okay. So why is this one? So if you actually see, what is your UR? UR equal to 1 by R dou psi by dou theta, right? So if you do this one, you are getting U cos theta plus Q divided by 2 pi R. That is correct only, no? Similarly, U theta. U theta is dou psi by dou R or minus dou psi by dou R, right? So this will give me minus U sin theta. Only this will contribute, isn't it? So this is also we know, that's what we have, right? Minus u sin theta. Minus u sin theta and this one. So that psi is correct. So to show this answer, you calculate whichever way you like. Just check dr by ur equal to r d theta by u theta, or that way, or just use the stream functions. You get from this, no? These two you solve. Try to get your psi. Just solve these two equations, you get your psi. You know what is
Yes,
ur,
sir.
you know what is u theta. So you
Yes, sir,
will get
that-
this one. Okay, this is a reverse way. Okay, we are only checking. So I'm just okay. So you calculate. So if I do this exercise, time will go. So this is what is your psi. So once this is your psi, what is your stagnation point? What is your psi value at q by 2 pi u comma pi? What is my psi value? Psi equal to, what is the psi value you get? Can you calculate? U r is q divided by 2 pi u. Okay, sin theta. Sin theta is sin pi, right? That will go
whole 0 and q.
q times theta is pi divided by 2 pi. So pi goes. This is anyway
Q
0.
by
So
2. Q by 2, sir.
q by 2. So psi is q by 2. So the is there any it should be, right? So there should be some streamline passing through this point, isn't it? So the streamline passing through this the stagnation point 2 pi u pi is, what is that one? Psi equal to whatever this constant is. It is same everywhere, right? So psi of r theta is u r cos theta is psi of r theta equal to this q by 2, isn't it? So that is psi of r theta is basically u r sin theta plus q theta by 2 pi equal to q by 2. So this is the curve. This is actually curve in the plane. So that is the curve which is your streamline passing through the point, stagnation point, this one. So if you actually simplify this one, r equal to, so you bring this that side, so you will get r equal to q by 2. So what is this one? This q by 2 minus q theta by 2 pi. This whole divided by 1 by u sin theta. Okay, so you try to take the LCM. So you'll have a 2 pi u sin theta. So what happens here? Pi here. So q into q pi minus q theta. So pi minus theta. Q is common. This is what is your r. This is the equation that you will get. So now you will see what happens at theta equal to 0. Where is that one? So what? So you see, as theta is equal to 0, this is basically sin 0, 0. What happens at sin 0? Is this correct? Yeah, this is correct, right? So what is your r at theta equal to 0? R is infinity, right?
Yes, sir. Sin 0. Yes, sir. Sin 0 is 0.
Yeah. So that,
If we put theta equal to
what is the
2
meaning?
pi
What is
pi.
the meaning of that? Theta equal to 0, and r is also there. R is finite. R is finite. Theta equal to 0. So r cannot be finite, right? At theta equal to 0. That means it is not there. There is nothing there at infinity and theta equal to 0. Right?
Yes,
Now you
sir.
fix your r. Fix your r. If you fix on theta direction, so you will know, right? So how do you see this curve? This is the curve. This is the streamline curve. The plane passing through the stagnation point. So if I draw, I think maybe draw, if I draw this, so this is your stagnation points. This will go like this. So how do you see this one? Can you see this one? This is your stagnation point. And how do you see this one? This is like going like this. This is a parabolic way. So how do you see this one? This is actually So at pi equal to at theta equal to pi, that is 0, right? At theta equal to pi by 2, what is the value? It is 1, right? That you can easily see, right? So this is at theta equal to pi by 2. So theta equal to pi by 2, that is 2 pi u divided by pi by 2. Pi by 2, pi goes q by 4u. So that is your q by 4u. Isn't it? That is your r equal to q by 4u. At theta equal to this one. Okay. Now as theta you decrease, this is at pi by 2, right? Theta equal to pi by 2, this is the y line. As you decrease, and it is basically, it slowly, this numerator is decreasing and denominator is also decreasing, right? Some kind of balancing kind of thing. It's not straight line. It looks like straight line, but it is not. Okay, so something like this you can expect. At theta equal to 0, it is slowly, it is becoming 0. R is becoming infinite as it comes now. So R is never, so you will not reach. Okay, so something like, so it goes like this. So what happens at theta equal to this side and this side? So more than theta becomes more than pi, so it is going to be negative. Okay, so you are basically getting R is actually, what happens? But sin theta is also negative, no? That negative goes, it's symmetric. Symmetric, how do you see at least? Minus theta if you put it. Hello? How do you see this 0 to pi and pi to 2 pi? Right?
Yes, sir. Sir.
Yeah.
Sir, how theta equal to pi by 2 r equal to q by 4u? I calculated, sir. After that, how this point will come, sir? Like y-axis is theta and this
I
one is
think it's not. You're not checking. See, simply it has to come to yes. No, at theta equal to pi, it has to come to yes. And at theta equal to, for example, theta equal to 45. What is the 45 angle? So what at theta equal to 45? If you look at it, this is the only way, right? Pi by 4. Pi by 4 is 45. You know. At theta pi by 4, what is the value of r? Q into pi minus pi by 4, 3 pi by 4 divided by 2 pi times u times sin pi by 2 is 1 by root 2. So this pi goes, what is this one? This q divided by 8, right? 8u and 1 by root 2, so 3 root 2. So this is what it happens. Which one is bigger? Q by 4u or q by 4u is bigger, or this one is bigger? So basically 3 by 8 root 2 is bigger or 1 by 4 is bigger? Which one is bigger? Square it.
This one, 3 by root 2.
You simply put it so like this. So this is what. So 3 by root 2, this is bigger, right? So this is actually going. So it's going like that. Asymptotically, it goes to infinity, right? As it becomes here, theta is becoming 0. It actually that you cannot. It will go to infinity, right? See, this is small, and this is bigger. And if you further go down, this is bigger, and so on. It's going like that. Okay. Some kind of oval shape. Okay. See, oval is looking like this, right? So you cut this half and then allow it to go like this. It's going like this. It is increasing. Keep increasing. At theta equal to 0, as you further come down, it will somewhere hit. It's only hit at infinity. Convinced? Hello?
Yes, sir.
Let me draw now. So if you actually draw the thing, so you have a stagnation point, and this goes like oval, goes like that. Okay. And then you have at 0. At here, Here, everything, see, this is the stagnation point, right? This is the stagnation point of the flow. This is your streamline. This inside this flow, this is the, see, these streamlines will not cross this streamline psi equal to 0. That is the point. So all the streamlines, whatever here, so it goes. So if you actually see this one, this will go, okay, and this will go. This also will go like this, because there is this uniform flow is there at infinity that pushes this, all this, that is actually pushing, okay, that this will go in between this, okay. So nothing will cut, nothing will cut actually. So like that it will go, okay. So even what happens here also it will go simply like this. This is also streamline, right? Inside the flow. That's what I'm saying. This is your inside flow. So this will go like this, and this will go like this, and this will go, this pushes, and it will go like this. So this is what is happening inside this body. So psi equal to 0, these are all streamlines. Correct? Now what happens outside? Outside, all these things, this will not cross psi equal to 0. This will not psi equal to 0. They're all parallel. So if you want, you can draw this one. This is some, maybe I can draw it this in some other color if you want, but I don't. Yeah, where is there some color? So this is the color. You draw this color, nothing will cross. Inside flow, outside flow is they don't cross this red line. Okay, that is your stagnation through streamline passing through the stagnation point. So basically, what is happening is ux. If you convert this into ux, so where is it? Black, no? So this is your ux, and you have a source. You combine them. So this is what is happening. Okay. So what is the direction? How do you see the direction now? Direction of the flow, how do you calculate? Obviously, no, this is the direction that usually you can see. So now based on that UR calculations you can do, right? Between 0 to pi by 2, you see it is always positive, it's moving away from the thing. So even inside also it is going to be like that. Inside, what is U theta? What is UR and U theta? So just calculate and see. What is your UR? So UR is this minus U sin theta. Clockwise, anti-clockwise, you don't worry, because it's not rotating, you can't see. So whether it is away, moving away or not, you can see from here, right? UR, U cos theta divided by Q by 2 pi R. U cos theta plus Q by 2 pi R. So this is what is your UR component. So you look at theta equal to 0. So what happens? At theta equal to 0.
U plus Q by 2 pi R is equal to.
When you come very close, no? So theta is between 0 to 2 pi. Let us say this takes the positive and negative values. But Q divided by 2 pi R, what happens? Q is positive, 2 pi R is positive. But as you come very close to 0, okay, as R is very close to 0, then this quantity is bigger, right? Isn't it?
Yes, sir.
So inside is this one. Outside, what happens? As outside means you are going bigger value. So for example, you want to look at here. This is bigger value of alpha R, right? This is your big value of R. So this you can ignore. And what happens to this one? So at theta equal to, so stagnation point at theta equal to pi by 2, what is the value you get? This is 0, right? This is Q by 2. That means at theta equal to 0, cos pi by 2 value is 0, right? So this here cos theta value is 0, cos theta value is 0, and theta equal to 0, u is, that is basically cos 0, that is 1. U, this is u plus, that is the maximum value is u, minimum value is 0 as you move from theta 0 to pi by 2, right? So Q by 2 pi R. Now if you are inside, there is a R is fixed, right? So if you are inside, R is fixed. So if you are outside, R is bigger. So away from R, you can easily see, and this is anyway going to be, so it's all positive, right? It's all positive, so it's away, moving away from the origin. Okay, but this side, if you look at it, all these things, the direction why I am putting this is coming towards the origin, right? So though it is here like going like this, but it is coming towards the origin, right? But if you increase R, this becoming smaller, and cos theta is between the pi by 2 to pi, what happens? Cos pi by 2 to pi by pi, cos pi by 2 is 0, and then it is going to be negative. So UR is negative, is basically coming towards the negative. So it's coming towards the origin only, no? As it moves, it is here away from origin. So as it moves, yeah, it is much closer, it's closer to 0 than away from that, right? So that is why this direction. Okay, followed?
Yes, sir.
Okay, so you don't see, you use theta, u theta, based on u theta is positive or negative, only clockwise or anti-clockwise, provided if it is making rounds. Otherwise, you look at only UR. UR is positive, it is moving away from origin. If UR is negative, it's coming towards the origin. Okay, this you keep in mind, so you can easily feel this one. So now what we do is we'll try to put this one. So I'm going to put what is that we what is that we did? Uniform flow plus source we added. Now I'm going to put two sources. So what do you expect? Uniform flow UX plus source at source or sink? Source, right? So you want source. Okay, source at which point you want to put source at? Q divided by 2 pi ln R, right? So ln R, where you are putting? So you're not putting not only at origin, so you make a distance of epsilon left side, that you put it as, so R plus epsilon, let's put it like epsilon cos theta. Okay, theta equal to pi here, right? Hello? Where
Yes.
exactly you're putting this value? R minus, what is epsilon cos theta? Suppose you want to put it here. So this is your 0. Okay. So at this point, I want source. So that you have, it will go like this, your stagnation point, passing through the stagnation point. So here I want to put sink with epsilon distance. Okay. Source and sink, you put it, allow the uniform flow. So what is the source here? What is this value? ln R minus 0, no? So what is the value here? Epsilon?
ln R minus epsilon, sir.
R plus epsilon, right? So this here, this side.
Yes, sir. R plus S, sir.
R plus epsilon, right? So I'll put R plus epsilon, and then plus, what is the other one? We're going to add minus, right? So it's plus because Q is negative, I have to put minus, no? So because it is a sink, Q ln of R minus epsilon. So that is at epsilon distance, divided by 2 pi. So this, if you consider as your phi r theta, so what do you expect? So what do you expect here? So you expect one uniform flow, and source, if you put it, goes like this, right? That flow goes like that, right? Actually, what exactly is it? Won't be here. So sorry, I think I wrongly draw here. So what should, where is your stagnation point? It will be somewhere here, no? Left side to the source, and it will go like that, isn't it? Similarly, when you take the minus thing, you try to calculate the uniform plus sink. It is exactly opposite. Your stagnation point, if you calculate somewhere here, it will calculate. So it is going to come like this. Okay. So now this together will be looking like oval. So you have a uniform flow minus, this is your, you put your source here, you put your sink here, this is your 0, this is your epsilon distance here. So this goes, this some kind of oval kind of shape. Okay, so outer things, this will not, this is your stagnation, this is your streamline with stagnation points. These are the 2 points, these are the 2 stagnation points passing through this. Passing through this, you will have a, this is your streamline. This divides the flow inside and outside. So what is inside? What actually is happening inside? It go like this, right? It goes like this, and here everything whatever goes, it will go inside here only, no? It will go finally here only, and whatever comes, that will come like this. Whatever goes like this, it will come like this. So somewhere inside goes, it will be like that. Outside flow, it will be going like this. So this inside, whatever now you have, this is the oval. If you want, if you have a cylinder of oval type, okay. If you have a cylinder of oval type, so you can consider source and sink at some distance, okay. So that you have your ux, and this is your, this is the flow. This is the flow path. This thing where you have this stagnation point. This is your streamline passing through the stagnation point that divides the flow inside and outside. Okay. So the whatever is Q and this source and sink, if you remove and you put it as a cylinder, some solid cylinder, if you put it inside, doesn't matter, no. So you can replace. You can just remove the sink and source, and whatever the flow inside, separated inside, now that you can think of, and there is nothing is flowing inside, right? So this is your this is your streamline passing through the stagnation point. So no, all these streamlines will never cross this line. So that is basically something like you are looking at solid cylinder of oval type. Okay, in that case, you put basically some epsilon. If you put it, depending on the epsilon, you will get a oval shape you are getting. But if you take epsilon goes to 0, as epsilon goes to 0, this oval becomes circle. So that is exactly what you do. So what happens when source and sink put together and epsilon goes to 0? That is your doublet. So implies uniform flow plus doublet as your phi. So that is if you consider okay, this physical. So this is your stream velocity potential will become ux plus this doublet. What is the doublet now? What is the doublet flow for you? Yes. What is your doublet? Cos theta by r, no?
Yes, sir.
Cos theta by r, some gamma, some lambda we put it, no? So this is what we have put it. So with your where lambda is that q times epsilon, limit epsilon goes to 0. This is a constant, okay? That is your lambda, okay? So there's lambda is basically constant. This is how you put it. That is your what is that one? That is a doublet strength. We call this doublet strength. Okay. So with this, now you can get again what is your UR, what is your U theta, what is your UR? So UR cos theta. So what is your UR in this case?
Sir,
What is your
lambda minus lambda cos theta by r square.
Yeah. So UR equal to UR U cos theta, right? Dou phi by dou r, no?
Yes, sir.
Plus
Yes, sir. Yes,
what you
equal
get here?
to
Minus lambda times
minus lambda. Yes, sir.
theta by 1 by r. If you differentiate, minus 1 by r square. That's why minus. So this is what is your UR, and U theta is what is U
1
theta
by
now?
r.
Minus U sin
1.
theta, like earlier, and this becomes cos theta becomes minus, right? Minus lambda. Cos theta becomes minus sin theta divided by r as it is. And you have 1 by r is there, right?
R square, so it will become R square.
R square. Okay, so that's
Yes,
what
sir.
you have. So 1 by r theta. 1 by r u r cos theta. Cos theta becomes sin theta. So that's my basically. Oh, everywhere you have cos theta. That you if you just make it sin theta, so that will do. Okay. The r goes in the first place. So this becomes r cos theta. So r goes here, u cos theta, that's what it becomes. So this is what you have. So again, to understand this flow, we again do the stagnation point. What is the stagnation point here? Can you give the stagnation point? See, now I have a doublet. It is not just a stagnation point. So what I want is basically your motivation is to look at the flow past the circular cylinder on the surface of the cylinder. That means on the circle, you want your boundary condition. What is the boundary condition that you want to see? You don't want any flow there, right? What is the boundary condition here? Solid cylinder. What is the boundary condition? What is the boundary condition? U dot n, right? N cap. What is that U dot n cap?
It is 0, sir.
Dou phi by dou r, right? That is your UR, which is equal to 0. Okay. So
Yes, sir.
UR has to be 0 on the boundary, on the circle, for example. Okay. On the surface of this uniform cylinder. Okay. So whatever you across, see, this is a cross section of r and theta only we are working. So z direction, so you have basically cylinder. So you look at this one, the stagnation point, if you call this r star and theta star. Okay, this is the stagnation point if you call it. So what exactly is happening? All those points, right? So where u are equal to 0. So you don't want to look at the stagnation point also, right? So if you actually look at the stagnation point, how do you get it? That's not easy to get, no? Because two equations to this thing, right? Like earlier, if you actually look for only for stagnation point, is it possible to get your thetas and theta and r here? Yes, it's not easy, no? It's just mixing of those things. That's why we can't do that. Okay, so we can't simply look for the stagnation point. If you do the stagnation point, I have to solve this and this. That is difficult. So, but you know what is our motivation? Motivation is to look for the flow past this circular cylinder. That is why I have a boundary condition. This is your boundary condition. That boundary condition, that is what you want to satisfy. So that is your UR equal to 0. This is your boundary condition. Boundary condition is UR equal to 0 at R equal to. So let us say the cylinder, it is of radius A. Right? So doublet becomes this circle, right? Let us say circle of radius A. So then you have a radius A at R equal to A. You want this boundary condition to satisfy. So if you want that to satisfy, what is the meaning of this? This cos theta minus lambda cos theta divided by A square equal to 0. What is the meaning of this? Cos theta cannot be 0. No, you have that is there for every theta. So that means what should be that? That lambda equal to U times A square. Your doublet strength should be this uniform flow into whatever the A square. Then only you will have that one. Okay. So a doublet anyway is an imaginary thing, right? Doublet strength things physically, because of that doublet only you are seeing inside the flow, right? Doublet makes you exactly what is your circle inside, right? That is where, so if you put the doublet inside, you will have a doublet. Okay, so inside you have a doublet flow, and exactly on the surface of this circle, you have this boundary condition, u are equal to 0. So with this strength, this lambda, you will take that one. So this lambda is the doublet strength. If you consider u into a square, then you have a boundary condition is satisfied, not for anything. Okay. So you want that you put this constraint, boundary condition is the constraint. If you put that, exactly you got the strength of the doublet. Strength of the doublet is fixed now. Any questions? Hello? Is it okay? Forward?
Yes, sir.
Then
I have to revise all those things, sir. Some.
fix. No, see, stagnation point alone you cannot solve because these are the two equations. No, earlier you have only you are able to solve. That is why you did. Here also you try to do, but you can't do. So, but you know the motivation of the problem. Problem is you want to solve flow past the cylinder. On the cylinder, you know that this is like a boundary condition. No? Normal velocity has to be 0. What is the normal velocity? Dou phi by dou r, because u equal to dou phi by dou x into n cap. N is, what is n cap? N cap direction is simply r direction only, no? R cap. So dou phi by
Yes,
dou
sir.
r, dou phi by dou x into r cap, r direction. So that is simply dou phi by dou r only, no? That is exactly your ur in polar coordinate. That is exactly what is ur. Ur equal to 0 if you put on the surface. This is true for all directions of r, right? So that is what you have. This is your boundary condition. Boundary condition fix your doublet strength. Okay. So
Yes, sir.
your doublet strength is there. Now you write what is your. So that's if you want your boundary condition to satisfy, your doublet strength will be u cos theta minus, that is your u cos theta, right? Minus now you got your lambda cos theta by r square. So u a square cos theta by r square. That is your ur. U theta is minus u sin theta minus again u a square sin theta by r square. Okay, so this implies if you write it neatly, so you'll have u is common. Okay, what exactly?
U cos theta. So you can take u cos theta common, sir.
Cos theta you can take it as common, and so that you have 1 minus a square by r square. This one, and u theta. Now if you put it u theta here, this will be minus u sin theta. I can take it out. This will be 1 plus a square by r square. This is what is your u or u theta components now. Okay. Now there is one small point that I want to make. So what is that you added? You added uniform flow plus this doublet, right? Doublet is after all cos theta by r, which is the solution of your Laplace equation. So what if I add something else? Other solutions. What are the other solutions like? Cos 2 theta divided by r square, all those things. Yes. Hello.
Yes, sir.
If you add a square by a2 divided by r square cos 2 theta, for example, if you add, still your boundary condition is satisfied, right? Is it satisfied? Still your boundary condition is satisfied or not? Cos 2 theta. It won't, right? On the surface, it won't satisfy. If you consider, you see, what exactly I'm trying to say is, as r goes to infinity, if you add, what is that? As r goes to infinity, what is happening? You still have your uniform flow because whatever you added doublet thing, lambda cos theta divided by, because divided by r goes to infinity, this is whatever you added doublet will not affect. So that means away from this cylinder thing, you basically have the only uniform flow. So if you want only that boundary condition, as at infinity boundary condition, only if you keep in mind, I can add further other solutions like a2 cos 2 theta divided by r square, cos 3 theta divided by r cube. All those solutions you can add, still that at infinity it affects. But if you apply this boundary condition, if you want to satisfy this circle boundary condition, then you need to add here. Right? Now, if you add, for example, this needs to be 0, right? So I have to add here also, right? Phi is this one. Phi, if you add a2 cos 2 theta divided by r square, then what is your ur? It is going to be 1 by r cube into cos 2 theta and so on, right? Ur. And if you want to satisfy finally ur equal to 0, what happens? cos theta, cos 2 theta, coefficients, everything has to be 0, right? At r equal to a. So there is an inconsistency. See, you cannot get it. You cannot really fix your, you will not be able to fix your lambda. You understand what I'm trying to say? Hello?
Yes, sir. Yes, sir.
See, lambda is after all your doublet. Doublet thing is okay. So you may fix some lambda, but there will be inconsistency. You try to add certain boundary, certain solutions of the Laplace equation, like 1 by r square and 1 by r cube and so on here. Then finally, when you are trying to get this boundary condition, do all those extra things that you do, that will give the inconsistency. So you will not get your solution at all. So this boundary condition will never be satisfied for all thetas. So only one solution, which is your doublet, that is your cos theta by r. So 1 by r power minus n cos n theta, in that n equal to 1 only will work. That is your doublet. In that only, for that only, you have a boundary condition naturally satisfied. That's what I want to tell you. Is there any questions here? Hello?
No, sir. No, sir.
Okay, so that's what you have. Now you have this. Okay, so at r equal to a on the surface, u r equal to 0, as you can easily see. What is your u theta? If you observe u theta, what is that you get? At r equal to, so minus u sin theta, 2u, right? That is your 2u sin theta. Now this is what is at r equal to a, right? So that on the surface, you have u r equal to 0, u theta
Yes,
is
sir. Minus 2u sin theta. Yes, sir.
yeah. So now can you see some direction? What is the stagnation point now? Stagnation points are where? Obviously, you can expect, no, physically you can expect only on the surface, right? So only on the surface of that solid cylinder, on the doublet somewhere, right? So let us put it at r equal to a, u r equal to 0 and u theta equal to 0. So at what values you will get this is equal to 0? U theta, you try to make it equal to 0.
Yes, sir. Theta equal to pi and 0.
Yeah, at theta equal to 0 and pi, we have u r equal to 0 and u theta is also equal to 0, right? So first we look at only one component. One component is 0 only on the surface, on the of that circle, right? But certain theta values, u theta is also 0. So those are the theta values, theta equal to 0 and theta equal to pi. So these are your stagnation points, basically.
We have two stagnation points, a comma 0 and a comma pi.
Exactly. So
Yes,
we passing through these stagnation points, whatever you are seeing. So this is your circle. So this is your, let me draw carefully. So this is your circle of radius 0. And these are the 2 points of stagnation points. Okay. So because your boundary condition is satisfied naturally, so that is why your stagnation, once you know your boundary condition is satisfied, through that way we can finally get the stagnation points. These are your stagnation points, S and S here. So passing through that, you have this one. So this is the boundary condition. Is this obviously if it's passing through, what is at u r equal at what are those points? R equal to a and theta equal to 0, right? And r equal to a and theta equal to pi. These are your stagnation points, right? So that is like a0 and a comma pi. So these are your stagnation points. So passing through this, at this value, what is your ur? Okay, what is your psi? Can you get your psi? Just like we did earlier. If you actually look for this flow, what is your psi? It's not easy, no? You need to get it.
Yes, sir.
Okay? So
We have to calculate EU.
you calculate that one and you try to calculate. If you calculate, that is fine. So you can actually see that is actually becoming circle. Okay. So passing through at this you put it, and finally you make it equal to that one, psi equal to whatever the value of psi. Okay, so what you're going to do is try calculate psi of r theta first. Okay, psi of xy basically psi of r theta. Okay, and then calculate psi at a comma 0 equal to what? Okay, you calculate. Okay, next calculate this one. Then from this, if you write it, you have r theta equal to psi at a comma 0. This is the curve in xy r theta plane. This is the basically what is this one? This is actually streamline passing through
A comma 0.
a comma 0. If at all it is there. Okay, if you find this one, if this comes as a circle, then this circle becomes your whatever circle of that is the surface of your cylinder is basically will be your streamlines. Otherwise, if you don't find, if this is not your circle, this curve is not circle, that means this passing through this you don't have any streamline. So take this as an exercise again. Okay, can you get this streamline and see whether this becomes a circle or not? So the question is this streamline, is this circle? Is this circle? What is the circle? Cross section of the cylinder. That is cross section of the cylinder that we are considering. So that is your question. Okay, so if you do that exercise, you will understand.
Okay, sir.
Okay, so I think I'll stop here. Have you followed whatever I'm trying to tell you?
Yes, sir.
So this is how you look at you can realize the flow past the cylinder. Okay, so far inside is anyway doublet, right? If it's a doublet, what will happen here? So finally, as epsilon goes to 0, so you have epsilon here, you have a source and sink, and finally you are allowing to be here, so it becomes this one. This is your doublet. So your doublet will be here. Okay, so the direction of the doublet will be how? What is the doublet direction? This is the source, this is the sink. So it is going in this direction, isn't it? Obvious, no? This you can easily see, right? See, sometimes you
Yes, sir.
feel the physics. Physics you can easily feel it. This is your source, this is your sink. You brought them together. So obviously whatever goes out of the source, it will go to the sink. So these are like circles when you bring them closer. So the uniform flow that you're considering from at infinity, that will go like this. So this is what is your flow past cylinder. Okay. Now, what is that we do? So why we do this one, first of all? So we are doing all this just to realize the flow. That is one thing, flow past the cylinder. And then you need to calculate the forces here and here. Okay, force in the x direction and force in the y direction. If you calculate, you will see that those are force in the horizontal direction is basically your drag. Force in the vertical direction is basically your lift. Okay, in reality, you may find some lift force here. So the lift force is there, or this drag force. Force in this direction, force in this direction. Okay, forces in both the direction. This is your lift. This is called lift, and this is your drag. If you actually calculate, okay, because of this uniform flow ux, you see that in this, because we're dealing with ideal fluid, there is no drag force in reality, but there is a drag force. Okay, so for that reason, this is called D'Alembert's paradox. Flow past uniform cylinder. Have you understood? Hello?
Yes, sir. Yes, sir.
What about others? Why no one responds? Can you just, okay, have you followed any questions up to here? Joe, is Joe around? Hello? Many are there. So only 1, 2, 3, 4, 5. What happened to remaining? Are you not able to follow or what? Rishabh?
Sir, I don't know, sir, why they are not responding.
But, okay, these are okay. This Sonam, any questions? Dhanush, Lakshmi Ganapati, Pragna, have you followed?
Yes, sir. Yes, sir.
It's fine. Okay, so it's fine. I'll stop here. Tomorrow I'll try to continue and what we do here. Okay. Someone wants to join. Who is Son? Okay, I'll just share this file with you and you just go through. So we'll try to, this is how we do. So the basic idea is to look at this drag force and lift force, which you calculate, we try to calculate. So how do you calculate the drag force here? Drag, so forces, for example, forces acting on the cylinder. What is the now we try to collect what you have done so far. So you have equations, right? So what are the equations that you are trying to solve? Del dot U, that is your mass conservation.